Okay, we're back. This is still chapter 37, but now we're looking at the digital imaging quality control. Um, and I wanted to say this is a much shorter section. It's a lot of terms, and really all I want you to know is the terms, what it's measuring, that sort of thing. So don't read too much into it. There's not too much math. I would also like to say that I want you to, next week, July 29th, we're not going to have an assignment that week, but I'm going to reopen the workbook questions, and most people didn't do those, the practice quizzes. I would like for you to take the week of July 29th, I think it is, and if you did not do the workbook questions, please do those because you're going to get 10 points for each workbook practice quiz. And that you have to actually try and do those. It's going to really help your grade. So that week, we're not going to have a new assignment. I'm just going to reopen those. Okay, so monitoring the digital acquisition system. This is the detector. So there are a few things. We're not going to get into this too much this semester because we're going to do it next semester. But there are field uniformity, which is checking to see if there are any light artifacts in the detector. Basically, you can take an image without anything on the detector with the cones open and visually inspect this. Erasure and ghosting are, this is caused when the detector doesn't completely erase the previous image. This is also called image lag or memory effect. Dark noise is unusual model or noise in the detector. And then with spatial resolution, you can use a wire mesh test or a bar test pattern. And basically, you're just looking for any kind of distortion or unsharpness that may be within the detector. And that would be caused by damage in the detector. Now we're going to move on to monitoring the display systems. So there's a QA and QC, as you can imagine, for the display monitor. And this has become extremely important because the radiologists read from the monitor. So since the display monitor is the weakest link, it's important to maintain quality. Otherwise, you risk misdiagnosing the images. And as you can see, there are several groups that have developed guidelines to monitor the quality for electronic images. So DICOM, remember, is Digital Imaging and Communication in Medicine. They have their standards that they've developed, guidelines. The American Association of Physicists in Medicine have also established guidelines, and that's the group we follow, because physicists check all of our equipment. There's also the Society of Motion Picture and Television Engineers, and then the American College of Radiology. So luminescence is basically the rate of light emitted from an LCD screen. The unit of luminous flux is the intensity of light perceived by the eye is measured in lumen, and this describes the power of light flow traveling through space. Steradian is just basically the 3D cone of light that's emitted from the display screen. And then the total rate of light emitted is measured in a unit of candela. And this describes the power of the light source, sort of like the power of a light bulb. Maximum luminescence of an LCD is about 800 lumen. And then the radiologist display monitors are anywhere from 500 to 600 lumen. The old view boxes, or light boxes as they were called, were 5 times brighter. So you can see the radiologist had, that's quite an adjustment for them. And then the American College of Radiology requires a minimum brightness of 250 lumen for display systems. So photometer and illuminance, those are two different terms. So a photometer is a device that's used to measure light intensity, where illuminance refers to the rate of light striking a surface. So for the photometer, there are all types measure light flux by the amount of current that's being generated through the photoelectric effect. And so you have photoresistors, photodiodes, and a photomultiplier tube, which was the old AEC device, actually. The concept that's applied to illuminance is the backlighting in the LCD or the room lighting that's actually striking the display monitor. So when you look at the unit of illuminance, or the lux, direct sunlight has 105 lux. And then when you compare that to typical office lighting, that's 75 to 100 lux, you can see that that's pretty close to direct sunlight. I always think of typical office lighting, or lux, as similar to a light bulb watts. So full moonlight is 10 lux. And when you get to a radiologist reading room, they're operating at 2 to 25 lux. So it's a very dark room. Luminance and contrast tests are basically a luminance response is basically a contrast test of brightness levels. Okay, the other thing that they're measuring in the monitor is the grayscale standard display function. And this is assigned digital values of the dynamic range that are in line with human perception. So what they're looking at in the grayscale is the just noticeable differences in the levels of gray. The luminance ratio is comparing the maximum lux to the minimum lux, and luminance uniformity is a consistency of single brightness level displayed across the screen. So it's just the uniformity of the brightness in your screen. Again, these are definitions. All you need to know is the definition. Ambient lighting and reflectance tests are measures of the light that's happening in the room. So you have two different types. There's diffuse reflectance, which is the ratio of brightness of the ambient light in the room being reflected, that should say, off the surface of the display monitor. So this is measuring the light coming from behind the monitor. Specular reflectance is a ratio of reflected brightness to the brightness of the light source. So this is going to be measuring the light coming from behind the viewer, or behind the radiologist. So it's just basically measuring the light that's in the room. Noise and resolution are two different things that are also measured or looked at on the monitor. Interestingly enough, there is no quantified guideline for acceptable levels of noise in the electronic image. But we do know that too much noise will reduce the visibility of low contrast objects in the image, so a radiologist might miss something if you have too much noise. And then both the American College of Radiology and then the physicist recommend a minimum resolution for electronically displayed images of 2.5. That's line pairs per millimeter. So that's pretty detailed resolution. And LCD monitors typically have very consistent and very uniform resolution, so they don't even require regular testing, which is why they're so fantastic in radiology. We've talked a little bit about this before, a dead pixel versus a stuck pixel. And so this is just whether the signal is on or off. So a dead pixel will appear as a white spot on the monitor, and a truly dead pixel means that it's no longer receiving a signal, so the signal is permanently off. A stuck pixel appears as a black spot on the monitor, and that's because it's continually receiving the signal. So that's just the difference between those two. But if you have too many dead pixels or stuck pixels, it's going to affect your image quality. Viewing angle is considered the biggest disadvantage to an LCD monitor because it's very limited. You can buy expensive LCD monitors and they have pixel elements that are slightly angled, and that just increases the viewing angle. And then most LCD monitors are self-calibrating, and they should be checked by measuring the stabilized brightness. So how it works is you would measure it every day for the first week, and then you would check it once a week for the first month, and then once a month for 3 months. And then luminance tests are usually done annually. Repeat analysis is the final portion of this section, and you can see when we used to use the old film screen systems, 60% of our repeats were due to technique errors or film chemical processing issues. Because if your image was too light or too dark, you had to repeat it. So with digital imaging, we don't have to repeat dark images. So we only have a 10% repeat rate that's caused by technique. So the majority of repeats in digital imaging are due to positioning errors. Now, the biggest disadvantage to a repeat analysis in digital imaging is it's difficult to perform an accurate repeat analysis because when the images are rejected, they're permanently lost. And then also, technologists are not always truthful in documenting why the image was repeated. So if they reject or repeat the image, they might say other instead of why they really had to repeat it. So that's the biggest, it's actually a big challenge trying to do a repeat analysis in digital. And that is that.